Hello, I am Frits de Mul and I would like to talk about the magnetic field of a long thin wire. This presentation is part of a series of presentations of topics of electromagnetism. The B field of a long wire. Suppose we have available a thin wire infinitely long carrying a current I. And the question is, calculate the B field in arbitrary points around the wire. First we have to perform analysis of the symmetry, then find an approach to the solution, do the calculations and draw some conclusions. And we have an appendix, angular integration. First, analysis and symmetry. Assume we have a thin wire infinitely long with a current I. The coordinate axes are with the z-axis parallel to the wire. And we have cylinder symmetry, and the cylinder coordinates are r, z and phi, and those coordinates are perpendicular. How is the field built up? We have the xyz axis, point P on the y-axis, and all the current elements contribute to the field B in point P. The field B in point P will have components in the x, y and z direction. Here we have the r, the phi and the z coordinates. And we will have the B coordinates here. Bx, by and bz, and bx is minus b phi. Approach to the solution. We have a current element I dl, and we have BO and Savart, and BO and Savart gives you dB is mu naught over 4 pi times IDL factorial product with ER over R squared, and dB will be in a plane perpendicular to the wire because of the factorial product. Note, we have R and factor ER here, and dB is perpendicular to ER. dL times ER means that we only have a phi component, and this is valid for all dL's in L, and this means that dB will be in the xy plane. Let's do the calculations. Here is the situation again with IDL, and we have the BO and Savart law. Calculate the vector product, then calculate R and calculate them both as f of z and insert and then integrate over z. Well, dl is this vector here times er is dz times the sine of the enclosed angle, and the enclosed angle is pi over 2 plus alpha, is pi over 2 plus alpha, with alpha here. And it means that it is dz times cosine alpha times E phi. Now, alpha, r and er are functions of z. And when we write those as functions of z, we can integrate over z. And when we do that, we have mu naught times I times dz over cosine alpha, and cosine alpha is written here, ip over the square root of z squared plus ip squared. That's the cosine of alpha, ip over r, and here is r squared. R squared, here, cosine alpha is here. And when you integrate, then you end up using the standard integrals with mu 0 I over 4 pi I yp. 4 pi over yp. Conclusions. The magnetic induction field in point P at the distance yp of the current wire is given by mu 0 times the current over 2 pi yp, and it is directed tangentially. There is cylinder symmetry, and B is independent of Z and X. Now, we have integrated over Z. There is also a possibility to integrate over the angle. Here we have the situation again. dB is Biot and Savart. And calculate the vector product and R both as functions of alpha instead of Z. Insert in dB and integrate. Well, dl is dz times sine pi over 2 plus alpha, because that was this angle here, pi over 2 plus alpha. Alpha is here. And that was dz cosine alpha times E phi. Now we calculate z, dz, r and er as functions of alpha. The z is ip times alpha, z is ip times alpha. So dz is ip d alpha over cosine squared alpha. R is ip divided by cosine alpha. And when we insert that, then we have mu naught I times the factorial in product ip over cosine times dz, ip over cosine squared alpha times the alpha here, and here is 4 pi times r squared, and this has to be multiplied by cosine alpha, and that's the cosine alpha here. Dz, that's this part, r is this part, cosine alpha is this part. And the integration leads to dB is mu naught I over 4 pi yp times cosine alpha d alpha. This is the expression for dB phi, and integrate over alpha is minus pi over 2 to plus pi over 2, and we end up again with mu naught y over 2 pi yp times E phi. And this is the end of this presentation.